Welcome back to Codex. Next up, we have another talk that was rescheduled from the 2022 JMM special session on recent advances in packing. Our speaker is Norah Tan, who is a graduate student at MIT. Norah is interested in quantum computing, quantum information, and coding theory. Today, she'll tell us about Grassmannian Packings. Take it away, Norah.
Thanks for the very nice introduction. So my name is Norah, and this is the work that I completed with Jingjing Hu, Qingjing Liang, and Robert Quadratic while I was an undergrad at Duke, so last year. So we'll get started. So quantum codes are about computation and correction. So on one hand, we need these codes to prevent error from happening, and when they happen, we want to correct them. And on the other hand, we need to use these quantum codes to do corrections, such as the basic universal computations. But some gates under these codes are easy to implement, but some are hard. So how do we do universal computation? And how do we want to make gates? And how do they interact with codes? And moreover, there are some other requirements we want them to satisfy, such as fault tolerance, in addition to the universality. And they are all under this quantum codes the topic, and people have been investigating in these questions for years, and we hope that the Grassmannian packing may be as a mean to approach these problems and to review some information to the answers. So this talk will be separated into 3 parts. The first part is on some preliminaries of the quantum codes. We'll talk about, if you don't know what quantum computing is about, we'll just set you up from the beginning of what is a quantum state and what is a quantum gate, and what is the stabilizer codes in the quantum context, and how do we interpret them using the code projectors and Pauli group. And the second part is about the Clifford hierarchy, which gives us a picture on universal quantum computation and fault tolerance computation. And the subsections include the Clifford group and some obstacles in this investigation. One is called Easton-Cornell theorem, and the other one is called Gottesman-Cornell theorem. And the third part will be all about Grassmannian packings. So this is the motivation about this talk, and let's get started. So quantum state, classically, when we do computation, we use bit as the basic computational unit, which is a binary digit of either 0 or 1. And when they multiply together, you get 1 + 1 = 0. However, in quantum computation, we use something called quantum bit, which is a qubit. And for a single qubit, it is a 2-dimensional Hilbert space over the complex space. And because it is a space, so we have bases for it. And the basis we choose to begin with is called computational basis, this 0 and this 1. So we call it a qubit 0 and a qubit 1. And they are just unit vector. And you can see with the linear combination, you can find with the linear combination where this alpha and beta has a norm of 1, you can they are all the single qubit pure states. So these are all quantum states that can represent information. And we have a nice visualization called block sphere that so on every point on the surface of the sphere correspond to a quantum state. And because of this nice normalization, and so you can do that. So you can see that the north pole of the z-axis is our 0 state, the qubit 0 state, and the south pole is the qubit 1 state. And every linear combination is a point on the surface of the sphere. So when we generalize this concept to n qubits, so classically that is n bit, which just 0, 1, 0, 0, 0, 0, 1. So you just put them together. So in qubits, we tensor them up. So this V0 and Vn-1, they're all 1 qubit in this form. And then when we tensor them up, they grow exponentially. The size of this quantum state grow exponentially, and there are just a lot of possibilities in them. So let's see one example. If we tensor a qubit 0 state and a qubit 1 state together, we'll get another norm 1 complex vector. Like it is essentially complex, and this is another quantum. This is a 2 qubit pure state. And if we write them into a linear combination, so this example is also a computational basis for the 2 qubit state. So if we write a general n qubit pure state as a linear combination of these basis state, it can be written in this form, a similar form, and the coefficients also has a norm of 1. So these are the quantum states. And what about quantum operations? So classically, we have, for example, also many kinds of gates like AND gate, NOT gate, OR gate, and quantum computation. They are unitary matrices because unitary matrices preserve the norm. So when you apply a unitary gate on the state, you will still get a valid norm 1 state. And we quantumly, we also have the bit flip operation, which is a NOT. So when you apply a x on a 0 state, you get a 1. When you apply x on a 1 state, you get 0. We also have something called a phase flip, which means that we will just apply a phase -1 to the state 1 if we are like applying it to z1 like equal to -1, but it does not change the value of the 0 state. So you only flip the phase when it is a 1. Some other quantum operations that are important are these 2 gates, so Hadamard gate and the phase gate. So phase gate, you can think of this phase as a square root to the z gate. So the first 3 bullet points are all single qubit operations. And when we evolve to multi-qubit operations, one example to begin with is this controlled NOT gate. So it applies on 2 qubits. One is called the control qubit, and the other one is called the target qubit. So the CNOT gate will flip the target qubit if and only if the control qubit is a 1. So if it applies onto this 1 0, it will give 1 1. It will flip the target because the control is a 1. And this is a valid unitary operation. So it's a valid quantum operator. So you can write it in a matrix that look like this. Some other examples of the quantum operators that are for multi-qubit is very straightforward. You can just tensor them up. You can just tensor the subsystems up to get a valid multi-qubit gate. And then we have the concept of a Pauli group. And so for single qubit Pauli group, it is generated by the X, Z, and Y operators. And the multi-qubit Pauli group is the tensor product of the n matrices in the single qubit. So you have like n qubits for the Pauli group. And another way to think about the Pauli group is, so we have a notation of D of AB, where A and B are both length n vectors, binary vectors. So and then you apply these vectors as the exponent to X, Z matrices that are for 1 qubit. And they are, if we consider the set of D of AB on n qubit, they are equivalent to our previous definition in the tensor product. And we also care about Hermitian operators. So we'll also define Hermitian Paulis, where you just add a phase in the front of this D of AB to make it Hermitian. And all all the Hermitian Pauli operators, they form an orthonormal basis for any n by n complex matrix under the normalized Hilbert-Schmidt inner product. So it means that like every complex matrix can be written in a linear combination in the basis of Hermitian Pauli operators. So after we talk about quantum operations, here comes the quantum codes. And for stabilizer code, we start with something called a stabilizer group. And the stabilizer group is generated by R commuting Pauli operators. So S look like this. The Pauli operators we just talked about, we just denoted as E of AB, and there are R of them. And the stabilizer code is a code space that is stabilized by this group, which means that like you apply G psi equal to psi. So it is stabilized by this entire group. And in this way, we can provide redundancy to this space because it is a subspace that lives in the entire space. So we can encode n minus r logical qubits into n physical qubits. So our stabilizers, they are of size 2 to the n. But the stabilizer group is of size r, and the dimension of the space that is stabilized by it is 2 to the n minus r. So there is a redundancy of r, which allow us to have tolerance against errors. And that is also the essential thing about error correction. So because we have this code space, and we can have projectors. And the projectors, for a single Pauli projector, it looks like this. I'm plus mu E of AB over 2, which project onto this plus minus eigenspace of E of AB, because this is like unitary and Hermitian. And if we multiply multiple single Pauli projectors together, and if this E of AB are the Pauli operators are the stabilizers, then we can have this code projector that project onto the code space of our code, onto the code space. And we can recall that we say this well expansion can give us what any matrix look like in the Pauli basis. We can expand this, we can interpret this coefficient, this trace, as an addition of this of the two components, where every component is a code subspace, is a code projector, and onto the plus eigenspace and the minus eigenspace. So now we're done with the preliminaries of quantum codes and moving on to the Clifford hierarchy. And the Clifford hierarchy starts with the Clifford group. And the Clifford group is the normalizer of the Pauli group, where you apply it by conjugation, you stay on the Pauli group, you still stay in the Pauli group. And it is generated by 3 gates that we've talked about, which is head-mark, phase, and C-naught. But this is not a universal gate set, which means that not every quantum operation, unitary, can be represented using, can be written as a product using these only three gates. So, and this Gottesman-Cornell theorem states that the circuit consists of only gates from the Clifford group can be perfectly simulated in polynomial time on a probabilistic classical computer, which means that we can just, these circuits do not provide us with quantum advantage, because essentially we can just simulate them very efficiently. So we need to focus on the gates that are non-Clifford, that are outside of the Clifford group. And interestingly enough, so with one addition gate, you can obtain any universal gate set. And this gate is called a T gate. And as I said, the phase gate can be think of a square root of the Pauli Z gate. And the T gate can be think of the square root of a phase gate. And this will become universal, meaning that every unitary can be written as a product using this 4 gates. However, there's one more obstacle. There's another, okay, as I said, this means that we need to focus on the non-Clifford gates because they are important to achieving quantum advantage. And here's another obstacles. It's called Easton-Canale theorem, which says that no quantum error correcting code can transversally implement any universal gate set. So here, transversally just is a convenient term for fault tolerance. So, which means that fault tolerance, universality, quantum code, they somehow don't coexist. So you need to find ways to get around with it while we choose to focus on the non-Clifford gates. And the Clifford hierarchy is describe a family of unitary gates, but are not every one of them, but a family structure of them that hopefully we can use this structure to review some information as, about non-Clifford gate and how do we get around with codes, universality, and fault tolerance. So the hierarchy looks like this. So the first level is all the Pauli matrices, and the second level are all the Clifford matrices, and the third level and above are defined recursively. So which means that if we start with the element in the L level, then you apply conjugation on the Pauli group by this element, you stay in its previous level. So the Clifford group, they normalize the Pauli group, so they still stay in the Pauli group after the conjugation. And the third level is that you stay in the Clifford group after the conjugation. And this T gate is precisely lives in the third level. And another interesting fact is that as we said, a Clifford group is not in universal gate set, but with one addition element from outside of the Clifford group, but still lives in the Clifford hierarchy, you will obtain a universal gate set. So we'll focus mostly on the third level for today's talk. Here's another concept of T, another identity of T, is that it is also a quadratic form gate. So quadratic form diagonal gates is a family of groups that live in the Clifford hierarchy. So the Clifford hierarchy, every level is not a group, but this is a group in the Clifford hierarchy. And they are all diagonal unitaries. And each entry is something look like this C sub L to the VRV transpose. And this, and the C sub L is the root of a unity, and this R is a symmetric matrix, so which make the VRV transpose a quadratic form. And when we are at level 3, this T gate is precisely a QFD gate because it is also diagonal. And every all the diagonal unitaries, quadratic form, they live in the same level of the Clifford hierarchy. So a natural question to ask is what happens if we apply these QFD gates on our codes? And an easy question to start with is we just apply it by conjugation on our single Pauli projector. And we can also expand and get another projector with the coefficients called PFAD. And PFAD, simplify it as this, when we notice when we are at level 3, this PFAD can only be 0 or plus minus 2 to the k or plus minus I 2 to the k for the same k. And another observation is that we notice band functions F can provide examples of all the non-zero PFAD that satisfy 1. And band functions are the Boolean functions that are maximally far away from any Boolean functions, and they can be connected back to the second order Reed-Muller code, which connect back to the quadratic form that we initially defined on this on our quadratic form gates. So now we move on to Grassmannian packing. So the packing problem, the most classic packing problem is we want to arrange m-dimensional subspaces of t-dimensional complex space so that the subspaces are far away from each other with respect to some metric. And these subspaces live in a space that's called Grassmannian space. And each subspace can be associated with a unique orthogonal projector. And the chordal distance between two subspaces, PQ, can be calculated as m minus trace of the two projectors, and which is a like you can also write it in the matrix norm form. And recall our definition of projectors, the single Pauli projectors that will project onto the +1 or -1 eigenspace of the Pauli operator. And the co-projectors is that you take all the stabilizers and then from stabilizer group, and then you multiply these single Pauli projectors together, and it will project onto the our code subspace. And our goal is to try to characterize the distance between subspaces after the conjugations of different operators on the same level of the Clifford hierarchy. So this Clifford hierarchy gives us a family of unitaries, and we like to see how they interact with the code spaces. So the way you apply a unitary, like an operator, on a code space is by conjugation. So this is a bit different from what we said at the beginning, where you just apply u to the state, because the state is a vector, so you can multiply u with the state. But now we have a code space which is a matrix, so you need to apply it by conjugation. So this is our goal, and another tool that we use is the theorem proposed by Conway, Hardin, and Sloan in 1990s. Hello.
Hello.
Hello. If there's a question.
I think there may have been an error. Go ahead and
okay, cool. So they said that there's an isometric embedding between the complex Grassmannian space with the chordal distance and the surface of a sphere in the Euclidean space with Euclidean distance, which means that every projector, they initially proposed it in the real space, and but you can generalize into complex space. So this means that every in our quantum code context, every code projector can be associated with a point on the surface of a sphere with some radius. And the radius of the sphere can be calculated as this, and this dimension d can be also calculated, and it kind of grows very fast as t increases. And we will study 3 cases, and the first 2 cases are all about second level Clifford. So the first case, we have n qubit and n qubits, and the code spaces we consider are all single Pauli operators. So the EFAB can be anything, and these subspaces live in a Grassmannian space of G of 2 to the n to the n-1, and when we have only 1 qubit, this is exactly the block sphere. So because this t is 2, and then 2 square minus 1, so d equal to 3. And you can see that the distance, if we plug it in the formula on the previous slide, you can see that on the 2 vertices, these 2 projectors are 2r away from each other. So r is the radius. So they are at the North Pole and South Pole, right opposite antipotent points to each other. And all the other points are on the equator for higher dimensional space in this sphere. So they are a really regular shape. And So this is exactly what we initially described in the first slide of the block sphere, where instead of having every point as a vector, you had it as a matrix, and these vertices are our code projector. And the second case is we consider the product of more single Pauli operators. So we consider there are n of them. So we exhaust the physical space. So we also still have n qubit, and we have n products of the single Pauli projectors. So the Grassmannian space is G of 2 to the n 1. So there's only one possible state in the space that we preserve. And it turns out this is a generalized idea for block sphere of multiple qubit states. So let's see what happened when n equal to 2. This is the state where we still can visualize, see how things are going. So because when n equal to 2, we have the product of 2 single Pauli projectors, and we consider them as A1, B1, and A2, B2, and we have this plus and minus for the different signings. So we have plus, 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 minus, minus, plus, minus, minus. There are 4 of them. And if we calculate the distance between these two, any two of the subspaces, and we calculate the radius r of the sphere of this embedding, we can see that they actually are the vertices of a tetrahedron. So you have this origin where the origin to every vertex is the radius r. And you can generalize this to more qubits. And the third case is focused on third level Clifford. So as I said, the first two cases focus on the second level, because if we apply by conjugation of the Clifford elements on this Pauli group, we still get a code projector. Is because when you apply by conjugation of a Clifford element, you still stay in the Pauli group, so you don't really switch outside of the code spaces. But when we move on to higher levels of the Clifford hierarchy, it will get more complicated, and you will switch out of the code space. So we start with an easy case where the third level Clifford elements acting on a single Pauli projector by conjugation. We're only one Pauli projector, not the product of multiple Pauli projectors. And recall that the definition for third level is that by applying conjugation, you stay in the Clifford group, but not Pauli. So it will get switched out. And the distance between one single Pauli projector that we start with and the resulting code projector after we apply the conjugation looks something like this. And we notice that this trace E of AB is exactly the Pauli coefficients in the Pauli expansion. So if we expand out this U A of B, U of AB, U dagger, this trace is exactly the coefficient, and it is a traceless and Hermitian second level Clifford. And this means that if we can fix this second level element, U of EAB dagger, U dagger, then we can locate where it is on the sphere by calculating its distance with every other vertex. So we just change this AB to CD, but this is a fixed second level element. And if we take n equal to 1 as example, we will see that this is our same block sphere where the blue points are the points in the case 1 study. And these red points are all the possible locations of gates after you apply a third level. These red points are all the only possible locations, and they are exactly the midpoints because the Pauli expansion of a traceless and Hermitian second level Clifford, we know what we know what it look like, because people have been studying Clifford second level for a while, but we don't really know what it is outside of second level. So this is what it looked like in the third level for n equal to 2. And if you goes upper in the levels, you will have more complicated possibilities for where these projectors can lie on. And we hope that this could be the Grassmannian Packings can be an approach to potentially tackle the Clifford hierarchy and potentially tackle how we can use quantum codes to do universal computation and fault tolerance computation. So that is all for today. And is there any questions?
Great. Well, let's be sure to react appropriately by smashing a button of sorts. And I'll pause the recording here.